Hi, today we are going to take a look at this aircraft indicator. The thing is a torque indicator which was used in a Fokker F-50 aircraft. There is a vertical tape indicator here. This white arrow should be a bug, should be activated by this knob. And there is also a digital indication. And there is here a manual annunciator. And the thing was repaired. There is a code or maybe a date, I don't know. And here there is a sticker for software revision. So we should find a microprocessor inside. The thing was manufactured by Amtech, and this unit was manufactured in '86. And there is here a circular connector. First, let's see what is inside, and after I will try to make it work after a reverse engineering. It should be interesting. Okay, look at that, very beautiful. So there is effectively a microprocessor. So this is the EEPROM, which contains the code. Okay, so this is an ATC49 from NEC. We have here a 2AD7542. So I guess that we have here two DAC. We have two op-amps, okay, which permits to convert the current output of each DAC into a voltage. So here we have a 4024, 4060, two op-amps. Here there is an obscure IC. So actually this is not an op-amp but a comparator, a dual comparator, an LM193. And here this is an op-amp, an LF156. Okay, and here there is an LM158. Okay, on the other side there is a beautiful electromechanical assembly. Okay, so there is one tape here, the white one for the torque indication, and another one here for the bug. Okay, so we have a DC motor, okay, which is linked to this gear. Okay, so we have the feedback potentiometer and the motor for the servo control. So we have two servo controls. So this is the reason of these two DAC here. And there is a smaller potentiometer for the bug and a similar DC motor, okay, for the second servo control here. Okay, so here we have the annunciator and this rotary switch, okay, which is linked effectively to this thing here. There is a small push button, the bulb is here, and there is a digital display. On the second board, it seems that we have the power supply and the servo amplifiers. So we can see these two cables here. Okay, so they are connected to the DC motors and the feedback potentiometer. So we can see two identical circuits. We can see here a 78S40. So I think that this is the pulse width modulation controller. And we have here a quad op amp and some trimmers. And the servo amplifiers use this part. It's a CA30. I cannot read 3080 or 60. 4080A. Okay, it's a very nice unit, a very nice construction. It is possible to disconnect everything. So I think it is possible to remove the cable from that side. So this is the front end actually. So this is the input of the device. I assume that we have an ARINC 429 interface here. Okay, it should be interesting to do the reverse engineering of this complete unit. And it can be also interesting to do a reverse engineering of the code itself here. I did the complete reverse engineering of this unit. So there is one interesting thing on that unit, which is the servo control amplifier. It is something which is not common. So when you have a DC motor, you need to control the velocity of the motor, especially with this one. Actually, we need only 4 turns of the motor here for the complete range. So we can see also that the mass of that gear is minimum. So we can see the circular cuttings here. This was done in order to reduce the moment of inertia of the mechanical load. The servo control amplifier uses a particular technique in order to control the velocity of the motor. Okay, so this is the schematic diagram of the servo control amplifier. The motor is here. You can see here the general equation of the motor. So this is the voltage across the motor. So this is the DCR of the winding. So this is the current flowing through the motor. And there is here the back EMF. So there is a specific factor multiplied by the magnetic flux and multiplied by the velocity in radians per second. One solution which is used sometimes is to compensate this resistance by inserting here a circuit which permits to simulate a negative resistance. So it is not perfect, you cannot have 100% compensation, but you can have something like 80%. So this permits a much better velocity control. So here we have something which is different. In that system, the motor is used alternatively as a motor or as a generator. You can see that if the current is null here, the voltage across the motor is an image of the velocity of the motor. Actually, this is the generator. So this is the goal of this amplifier. So this is an OTA, a specific amplifier. There is a current output here, and there is a bias current input, pin 5. If this pin is left open, the amplifier actually is disabled, and we have a very high output impedance here. The motor can be isolated from the amplifier here. So you can see we have here a square wave generator. The frequency is approximately 600 Hz. Okay, so the output, and there is a square wave from minus 12 to plus 10 volts approximately. So we can see here we have a P-channel MOSFET. So this is actually a sample and hold. When the voltage is negative here, the amplifier is off. Okay, and this MOSFET is on. So therefore, across the capacitor, we have an image of the velocity. And when the voltage is positive here, the amplifier is on and the MOSFET is off. And in that case, the feedback of the amplifier corresponds to the voltage across the capacitor, which is an image of the velocity. So therefore, after a few cycles, the differential voltage here will be very low. And in that case, this voltage permits to drive the velocity of the motor. So this is an interesting technique. I have never seen this technique before. So here we have the output of the DAC. This is a negative voltage. This negative voltage is fed to this inverting amplifier, which gives a positive voltage as this output. And we have here the feedback potentiometer, which is also a positive voltage. So here there is an error voltage, which corresponds to the difference between the final position here and the activable position. So this error voltage is fed to this voltage to velocity converter we have seen. For the torque, there is also this circuit which permits to have an analog output on terminal G. And we have exactly the same circuit for the bug setting, except that we don't have the analog output. We can see here the ARINC 429 interface. The input is here, there is a differential amplifier and two comparators. This comparator gives a low level at the output when the differential input here is above 5 volts. The second one here gives a low level for negative input voltage, that is to say for low level bit. There are three outputs. This output is connected to the external interrupt of the microprocessor. Here we have a low level when the first byte is received, that is to say the label. Here we have a second signal which is activated when there is an error. And there is another signal here connected to T0 input of the microprocessor when another byte is received. Here we have the disassembly of the code for the interrupt. So here we have a read of the data. So therefore this interrupt corresponds to the reception of the label, and we can see that the label is saved on R2 register. Okay, so we can see that the label here R3 is added with value 5 and 0 is verified. That means that if the sum of the label and 5 equals 256, we have the first label. That is to say, a label of 251 in decimal. That is to say, 337 in octal, because you need also to permute all bits. So the first label, 337 in octal, corresponds actually to the engine rating. So this is actually the setting of the bug. If it is not the correct label, we have a jump to this address, and we can see that there is another addition with 80 in hexa. Okay, so we can see that we need to add 80 and 5, okay, to have 256. So that means 7B in hexa. Okay, so you permute all bits and you find 336 in octal. So this is the engine torque. Okay, so we have the two main labels, 337 for the bug setting and 336 for the torque. And we have a third label. We need to add 64. So that means 80 plus 5 plus 64. That means 233. So this gives a label of 17H. You permute all bits and you find a third label 350. At that time, we have the labels which are detected by this unit. We have effectively the engine torque for label 336 in octal. And we have here engine rating for 337. The next one is a label 350, which is here. So this is the maintenance label. Okay, it permits probably to perform some test and some verification during production or service. So there is also a GPS test award possibility. For the test, I have modified my ARINC 429 generator here in order to set the torque and the bug. It is possible to adjust the percentage by step of 5% using a page up and a page down case here. It is also possible to set the bug manually. You can see also that this display is actually an analog display. It's a kind of voltmeter which is connected to the output of the DAC. So it is strange that they didn't use a digital interface. That's all for this torque indicator. Thank you for watching and see you next time for another video. Bye bye.